Welcome back, folks. Still playing with the transients in a circuit. We're focusing on first order transient circuits. So those are going to be circuits that have one storage component in it. Sometimes we call them reactive components. Last video we had a capacitor and it was discharging. And we ended up with a particular form. We want to figure out how that capacitor charged in the first place, and we're going to look at the form of that solution as well. So it's kind of a similar kind of video. We've got to do some analysis. We've got to do a little bit of algebra, and I'm still going to be using separation and integration to find the solution to these differential equations, since I think that's what most people are going to be comfortable with, given I know that everybody's taken Calc 2 in this class. Okay, so charging capacitor. So it's going to look like this one. It has a voltage supply. I put a battery across the circuit. It's got some resistance, and it's got a capacitor over here. We can begin to develop the solution for this using a similar approach, and I'm going to use nodal. Usually when I see a capacitor, I tend to lean towards nodal, since what I'm interested in is the voltage across that capacitor. And nodal is looking for voltages. Okay, so let's see. We've got two non-reference nodes now. Okay, so this one is VS, and I could force myself to call it A and do some substitution, but why don't I just call that VS, because that is the voltage across the capacitor. It's going to just make our lives a little easier. And then this one over here, we have VC of T, right? That's the expression that we're after. We want to understand what the voltage across that capacitor is doing at different points in time. So I want to be able to evaluate that function at different points in time. Okay, passives get arbitrary current directions down and to the right. Okay, this one we leave alone. That's not passive, right? So if I'm treating this as a known, then I really only need one equation, and that's the equation that we're going to work with here. So I need to write a KCL. Right, write a KCL. This is a charging capacitor. KCL for VC of T for that node. Okay, this current's going in, so the voltage at the tail is a constant VS, minus the voltage at the tip is the voltage across that capacitor. And that's all going to be divided by R. Same thing we did before, right? Voltage at the tail minus voltage at the tip over the resistance. Okay, this current is leaving, and that's the current through the capacitor. So we need to use the capacitor equation again, C dV, C dt. Okay, those are the two currents going in and out of that node, so it's equal to 0. And there's your differential equation for this one. We need to find some expression for VC of T that makes this all be true. Okay, so if I took the derivative of it and multiplied it by C and subtracted that from all of this stuff, it needs to all work out to 0. So how do we find that? Well, we're going to separate and differentiate again. So we want to get all of our VCs on one side, and we want to get all of our T's on the other. So I'm going to bring this R up. I'm going to multiply both sides by R. Right, so this ends up being VS minus VC of T minus RC dVC of T over dt. Okay, and when I multiply 0 by R, I end up with 0. Okay, so once again, I wanted to collect my constants as cleanly as I could. Okay, so let's see. We're going to leave RC over here. We're going to bring VS and VC over to the other side. Okay, so leaving that there. Okay, and then bringing these over to the other side. So I've got to add VC of T to both sides, and I've got to subtract our constant VS. Okay. So still trying to get all of our VCs on the left and all of our T's on the right. So we've got to break some of this stuff up. I want to bring RC down for starters. So I'm going to divide both sides by negative RC. Okay, so negative RC ends up in the denominator there. And then we can also split up our derivative. Okay, so I can bring up into the numerator dt by multiplying the left and the right side by dt. Okay, getting closer. We've got to get this one all by itself, and we got to move it down over here. And we're going to do that just by taking this whole numerator, okay, and dividing both sides by it. And that leaves us over here with negative 1 over RC dt. That side should feel familiar. This side, we just have this additional constant term that's floating around with us. But we've effectively done what we need to do. We've gotten all of our t's on the right-hand side. We've gotten all of our vc's over on the left-hand side. All that's left to do is some integration. So similar limits of integration over here. We're going from 0 to t. So we got to make sure we change our variable of integration. And I'm actually going to change it in here since I kept the functional notation a little more consistently in this video. But we're going to integrate this side from VC at t equals 0 up to VC at some time t. All right, all that's left is the integral. I'm not going to leave that to you if you don't want to. I can certainly go ahead and do it for you. Okay, so we have the same kind of natural log over here, and we're going to have VC of tau minus VC of 0. Okay, I'm sorry, minus VS. My brain went too fast, faster than my pen in my mouth. Okay, we're going to evaluate that from VC of 0. Make my V a little nicer, to VC of t. All right, over here we have negative tau over RC, and we're going to evaluate that from 0 to lowercase t. Okay, so it looks similar. Here's the difference inside the logarithm, and that's going to change our form just a little bit, but not drastically. It's really not going to be too bad. Okay, so if you followed the last video. If you didn't, well, then you should go back and check that out and make sure you follow all the algebra I had to do and the little bit of calculus I had to do. Okay, so this is going to be the log of VC of t minus VS minus the log of VC of 0 minus VS. Okay, that's my left-hand side. And over here we're going to have negative t over RC minus 0 over RC. That drops to 0, so I'm not going to do that one anymore. We're going to use the same trig identity on the left-hand side of the equation and get ourselves down to the log of VC of t minus VS over VC of 0 minus VS. Okay, getting closer. And on the right-hand side, we have negative t over RC. Okay, still trying to solve for this one right here. And if we're trying to solve for that one, then we've got to get it out of the logarithm. And we're going to do that in a similar fashion to what we did in the previous video. We're going to make both sides of the equation, both sides of the equation, there we go, exponents of the natural log. Okay, so that's going to drop that out, and we're going to be stuck with that natural constant e on the right-hand side. Okay, so VC, let's just get this rewritten so it's a little cleaner. VC of t minus VS, VC of 0 minus VS, and e to the negative t over RC. on the right-hand side. Okay, still trying to get this term in the numerator separated out. So I'm going to multiply both sides by this denominator. Okay, so that's going to leave me with VC of t minus Vs on the left-hand side, and VC of 0 minus Vs. I'm putting it in brackets because I need to make sure that everything distributes cleanly. E to the negative t over RC. Whew. Getting there, getting there. Okay. All we got to do to get VC by itself is add Vs to both sides. So we're going to get Vs positive, right, plus VC of 0 minus Vs, all of that in front of e to the negative t over RC. Whew. Okay, so that's what we were after. And if you're paying really close attention, this one's a little bigger, a little uglier than the form of the solution from the previous video. But if you pay attention and compare those two, and I'm going to do that in a future video for you, coming up real soon, you're going to see that they have the same form generally, and we're going to use that form to try to solve it. Okay, so now we can charge a capacitor and we can discharge a capacitor. It's not our only storage element. We can do the same kinds of things with inductors. So I'm going to do 2 more videos. We're going to discharge an inductor, and then we are going to charge that inductor back up. If we can do those 4 types of things with these circuits, then we can solve any first order differential equation that describes the behavior of a transient circuit with a single storage component. So if we have 1 capacitor or 1 inductor, we're in good shape. Okay, so the inductor's coming up next. I know you're excited, and I can't even keep it. That requires a clown nose. I know you're excited. Okay, bear with me. We're going to start analyzing circuits with all of this stuff in a few videos, but we kind of got to go through it so that we know that it doesn't come out of nowhere. Ohm's law, KVL, KCL, capacitor, inductor equation. We're still using nodal. We're still using mesh. We're building off of all of the stuff that we've already done this semester. So let's keep going. Stay tuned and good luck.